I hope that we can still make some progress in time. And what I can say that based on today's questions, I offer you like a second pass where we can do more detailed analysis, yeah, and more detailed some exercises. And we can even work in doing some mentoring. Okay, so today I will be giving you an introduction to data analytics and artificial intelligence. I hope that with this one, I can give you enough excitement so that you can get participating with the world of analytics intelligence. Yeah. I wish I can see chatting so that if you have any question, you can ask me through the chat. Okay. So try to send me any question by chat, and I will be able to answer at the same time that I'm receiving the questions. Okay. Or you can also interrupt, but I think because we have several people connected, it's going to be more difficult. Okay, so the first set of introduction, this is the agenda that I have for today. Is I'm going to give you an introduction of what is this world of analytics, AI, and deep learning, and what is the relationship with the different other techniques such as statistics and predictive analytics, which they seem to be quite connected. By the way, Olanike, you can tell me how much time I have since I have already started late. So let me know how much I still have. Yeah? So I will then I will walk you through some case studies around reservoir, petrophysics, production, and seismic, which is a number of selected cases because there are thousands of cases today available. Then a little bit about digital transformation insights, and then some way forward in terms of getting involved, getting social, connecting through SPE and open source tools. Yeah? The first area to share with you is a quick overview of what is analytics and artificial intelligence. Pretty much used today in many things that we do in our world. And not only in oil and gas, but also in our day-to-day, our cell phones, our social media is fully loaded with artificial intelligence today. The overall process of artificial intelligence is a collection of statistical and learning tools. So these statistical and learning tools are very much founded on mathematics. So we have the statistical learning, cluster analysis, probabilistic learning, and we will learn how all these fit together into the actual presentation. Okay. So in oil and gas, we use this for pattern identification with historical data, for progressively improving the performance of our models of data, such as history match. We use it for knowledge discovery in data and images. So you see here a little bit cars and self-less driving, but it's very much used also in seismic and geological image identification. We can also use it to automate repetitive tasks. Okay, so this is a part of digital transformation. And we can also use it in the process of portfolio management, such as, for example, identifying candidates for workloads, identifying well locations. I don't know how to move the echo from my side. I'm in a small room, but I will try to lower the volume of my speaker then. Since I don't need to listen to you, so I'm going to lower the volume of my speaker to see. If you need to talk to me, just ask me a question.
Luigi, can you hear me, please?
Yes, I can hear you.
So, I was going to do this at the beginning, but it's fine now. What we intended to do was to leave all of the questions at the end so that you are not disrupted, and all of the questions will come later. I think that's fine, yeah? And please, can I ask everyone to, I don't know why the mute all doesn't seem to work properly. Please mute yourselves, please, and remove your videos, please, so we can only see Dr. Luigi. Thank you.
Okay, and then the other thing is that, I mean, I'm okay if you want me to go back to a particular slide or something that I'm presenting or you don't understand, feel free to put it in the chat, okay? If it is a quick question. And Olanike, how much time I have left?
Okay, so you started quite a bit late. So if we can make it a little bit quick,
Yes.
so that people can get back to their work and lunch and whatever else they have to do, if that's
I'm trying
okay
to
with
make
you.
it in the next 30 minutes or less. Yeah?
Okay, that'll be fine. Thank you.
Thank you. Okay, so these are the main uses in general we will go and discuss. The value proposition for artificial intelligence is, of course, to reduce the decision cycle, so make faster decisions with a well-informed collection of information, reducing the operating cost. So basically, that's how do we improve our business, reducing the human errors coming from multiple data handling manipulation, and deriving smarter decisions. So statistics, analytics, and AI, these are a number of interrelated topics that are typically used when we refer to today's artificial intelligence. So we are using, just to give you a historical context, statistics is a science of mathematics around data. And it started in the 700s, so close to the 8th century. So we have been using statistics, mainly deriving descriptive statistics, making inference from data, exploration data, the law of probability, classifying, etc. The next artificial intelligence appeared officially in the 50s when the revolution of basically cryptography. So during the World War, there was an interest to decipher crypto messages that were passing from all the different intelligence. And a number of techniques appear around reasoning, problem solving, knowledge representation, etc. The next one is machine learning, which appears in the 80s, which is a derivation fully related with statistics and artificial intelligence, but with the blow of artificial neural networks, decision trees, support versus machine, Bayesian networks, etc. So if the statistic has the tools that are the regression models, the logistic models, the PCA models or principal component analysis, discriminant analysis, etc., artificial intelligence had the problems around symbolic regression, search and optimization, and Bayesian networks. So these are the tools that came around this technology. And the last but not least is the deep learning concepts of automatic speech recognition, image recognition, visual arts, natural language processing, and recommender system. The main difference with all this evolution is the capability of handle more amount of data and to do more computations in the least amount of time. So in general, if a statistics is the math of data, so where a statistic focus on building models for creating or establishing an inference between the relationships between inputs and outputs, or between the data collected and the observation. Artificial intelligence focus more on the methods for incorporating any human intelligence into machines for via explicit programming. Okay, explicit programming means that if I have this, I do this. So if then else rules types. So, or I can build this number of combinational rules. So there is an overlap, but not everything in statistics is artificial intelligence, and not everything in artificial intelligence statistics, but it's definitely a clear overlap between them. So the next element in artificial intelligence that provided a lot of support was the appearance of probabilistic reasoning, the use of Bayesian network and the Bayes theorem, hidden Markov models, and Kalman filtering allow artificial intelligence to produce decisions more accurate and with more support than humans. So in the 50s, there was a lot of these programs that trying to mimic how people, for example, play chess, or how people will win another game that was programmed by human. The knowledge-based system came also along with the so-called case-based reasoning. The case-based reasoning refers to how do I use my systems. Somebody's not looking at the slide. Okay, everybody else is looking at the slide, right? Case-based reasoning, expert systems, and recommender system. We will talk more about this and as we talk about this slide. So this slide will take most of our talk just to give you a quick overview of the applications. In statistics, and also as part of the artificial intelligence, a lot of tools such as PCA, or principal component analysis, or what the so-called model dimensionality reduction, started to play an important role. So one of the applications of PCA is, for example, every time you take a picture and in your phone, the picture is probably 2 to 5 megabytes in size, but when you send it to somebody through WhatsApp, you probably sending as image that is 100K bytes. So the same image, but it's much less heavy in size. So this is so-called dimensionality reduction. It's a compressed version of your image. You still see the image, you still see the person, but then someone is not necessarily taking that amount of resources. Machine learning is that field of between statistics and artificial intelligence. Actually, it's a collection of tools that empowers computer system with the ability to learn from experience. So now we're focusing on what the previous systems, we were explicitly programming something. We were explicitly establishing a relationship between inputs and outputs. But now we want something that continuously learns from time to time. So using the reinforcement learning, how do I progressively improve the performance on a specific task focused on prediction? Then the number of tools that were selected for this are the artificial intelligence, multivariate regression, etc., and put it in the context of continuous learning. The other type of technique that helped a lot in this area was the search and optimization. So especially, for example, in our history matching process in reservoir engineering, we use a lot of search and optimization, and where we try to continuously and progressively aid of these models. The next set of, let's say, buzzwords that appear in this area was the analytics. The basic of analytics is that in how do we process huge amount of data, discovering databases. And this could be something by applying statistics, continuous learning, but a set of tools that allows me to get more from the data, transforming unstructured data in structured data, managing and massaging big amount of data. So, and with this one appears two classes of algorithms, which were the image processing and recognition, where all the analog to digital conversion appeared, and the digital processing, and also the text mining and natural language processing. This came out in a big area of improvement because we were able to massage big amounts of data in the sense of transforming text, big document text, categorize the text, cluster the information, create the proper concept entity extraction, do sentiment analysis, summarize the documents automatically without having the need to do explicitly a programming like that. The next area of interest is the deep learning. So deep learning sits in the center of statistics, artificial intelligence, and also machine learning. So the deep learning, as we will see later, is an evolution of the so-called neural networks, but in a different way, more complex problems and more advanced number of internal layers. It sits in the middle because it has enabled all of the artificial intelligence that we see today. Is the main area of continuous learning of the images, is how Google automatically recognizes the faces of the people when we upload a picture, or automatically we can see a fault identification in a seismic that has never been presented to a machine. In the artificial intelligence, there are two main areas of what we call artificial intelligence. The so-called general AI, or general artificial intelligence, which is a generalized capabilities of humans embedded into a machine. So this one is like trying to create like supercomputers or super brains, that were computer like, or the so-called machines that knows about everything, that we cannot recognize if it is a human or it's a machine. So that type of general type artificial intelligence, they're able to even try to solve a problem that has never been trained to do before. And the so-called narrow AI, which is specifically the ones that we work as engineering and in petroleum engineering, and is the one that is more common around industry. So these are specific applications that provide the ability to perform better than human in specific scopes. So we have in general, for example, image recognition, or remembering pictures, or recreating an artwork, or winning a game of something that you have never been performed. The other type of artificial intelligence that have been very common in industry are the robots. Robots are machines, automatas, that they can complete repetitive and complex tasks. They are called AI because you can embed a number of human-like activities, but they're somehow automatas or autonomous in a way that they do repetitive tasks and only that. They cannot do more than that. Control is an area of interest, or so-called the automatic control or automated control or process control, is the type of technologies that we use in refineries, in the field, in manufacturing, in order to automate the task continuously in continuously changing dynamic conditions. So it's different from robots, because the robots are like machines that do movement all the time based on conditions, but they're very related. Like in robotics, we have control theory applied, for example, for the movement of an arm or the movement of a robot. So they follow control theories technologies. And robots are also used in the control world. So they're very related. The next type of area of AI, which touches a lot of analytics, it touches the deep learning, and it's also part of artificial intelligence, is the so-called recommendation engines. So some of you have already done like purchases in Amazon, or purchases in the internet, or watching a movie through Netflix. So this system provides relevant suggestions based on the previous choices that you have made. So if you have bought this type of clothes, then, for example, then you should be somebody that had in this age range. Therefore, I'm going to recommend you to buy this additional concert ticket. So they make the connections automatically without being explicitly programmed. The next type of categories are the so-called bots and chatbots. So these are programs, so they are very similar to robots, but if a robot is a mechanical instrument, a chatbot is a software robot. Okay, so also called, so sometimes we have called to a bank or called to a particular help desk, and we talk to a robot. We talk to an autonomous program that is able to interact with systems as users, completing the so-called virtual task. Okay, and so we are able to provide a human like service without being exactly a human. And all of this is also being used more and more in the oil and gas. Okay. And the last but not least, that has done a lot of progress in part of the artificial intelligence is the so-called natural language processing and natural language generation. This is the process and analyze large amount of data of natural language data. So we're able to provide and understand a big level of a large volume in a short period of time without having the need of understanding what you are actually having. So for example, today we see translation engines. We have operators talking to a machine that is answering questions like if it was a human like on the other side. So all of these are part of this. So I prepared these slides for you just to give you an overview of the overall how all these different technologies interact. And for each of these, there are applications already going on in the oil and gas that will transform the way that we do oil and gas. Okay. Many of you have already listened perhaps about neural networks. You say, well, but neural networks are also they have been in the oil and gas, I believe, since the 80s. They were all neural networks. And what is the difference with deep learning? So deep learning, they're also neural networks, but let's say they are more complex neural networks. If a simple neural network has from 1 to 3 hidden layers, in the deep learning, we may have many hidden layers, and each hidden layer will have a different functions. In the neural network, we train all the layers at the same time. In the deep learning, we can have neural networks trained in different moments and with different type of data. The training duration in neural networks may be from minutes to hours. We expect to have a particular solution, while in deep learning, we use big computers, we use big infrastructure in order to train, and this training may last from days to several weeks. The number of input variables in deep learning is like three orders of magnitudes bigger than the neural networks. Okay. So this is one simple application, and I just bring you this very simple application of a well classification with machine learning. We have a field with a number of wells, and we have certain experience. Okay, this experience may come from operators, or it may come from a simulation model, or may come from a IIM model. So I have wells. We have certain rates. Okay, for example, this well with 1500 high water cut, medium GOR is the engineer, after doing all the analysis, has this well as healthy, and it proposes an action to increase the rate from this well. I have another well that is 1800 high water cut, high GOR. The well status is declared as sick, and the action here is to decrease the option, decrease the rate. I have another well with 1350, low water cut, high GOR. Well, status is healthy, but it is recommended to decrease the rate in order to avoid the well to become unhealthy. Another well with 1120, medium water cut, high water cut, and is sick, and the recommendation is to repair. And now I have the challenge to say, okay, I have a new well with 1400 with low water cut, low GOR, but I don't know what the status is, and I don't know what to do with the well. So these are the type of problems that I will take a machine learning model, I will get a classification, and the system will, and I have to break down into different stages. One is I have to determine the status, and then based on the status, given the prior conditions, I will declare an action in here. So this particular problem we are applying in, for example, in this company in ADNOC, and we are trying to identify from thousands of wells, describing the conditions of the particular, for example, wells that are inactive or wells that are currently producing, what is the status in terms of health status, and also an action move forward, either repair, recommend for squeezing, recommend for water shut off, recommend for sidetrack, or recommend for abandonment. The way that neural network work most of the time is we have what the so-called the input label data. When we say label data means that is data that I know. For example, in this case, the label data will be that given these three inputs, 1500, water cut high, GOR high, the labels are healthy, and given that it's healthy, the another label is increased. So here I have two problem solution. So I have all this label data I have, and then I have some new data here, the last value, into which I'm going to use this model for either validation or for prediction beyond my training data set. So I input data, I build the model, I use the model, and then I use new data in the future in order to exploit the use of this model into my real life situation. Okay. I will start to mention some examples of how these are being used in oil and gas. And I have here 4 slides describing a number of situations. And I will also here give you the paper reference number and how these are used in multiple areas. Yeah? Here. So the first paper is given by Andrei Popa. This paper here is, he has a collection of papers mainly for identifying candidates for workover and candidates for good quality wells in certain reservoirs. So what he presents here is a series of maps we see here. So he derived what is so-called the dynamic reservoir quality index. So dynamic reservoir quality index is a data-driven, let's say 3D quality that he finds connectivity between a static model and dynamic performance of the well. And then he compares this with the so-called heterogeneity index. So for those who are reservoir engineers and petrophysicists and geologists, you may be familiar with the so-called Lorentz coefficient, yeah, or which is the Lorentz plot. I'm sorry. So the Lorentz plot and the modified Lorentz plot, they provide sometimes certain measurement of the heterogeneity of the reservoir, and they provide a certain measurement of where the maximum storativity and flow capacity exists in the reservoir. Now, those elements are he proved in this paper that another data-driven reservoir quality index workflow, where he described this property. So this property here, what he called DRQI, is a property that connects flow components, storativity components, and dynamic performance components of the field, is able to be a better predictor of the well cumulative production along the life as in relationship with other variables. Like for example, if we do only saturation of oil, I have this value here, but I will probably place it in another area. If I look at temperature, because this is a field that has temperature related stimulation, then I will probably not fix it in there. But the DRQI, which is a combination of both resistivity, saturation, temperature, and dynamic conformance, is a better indicator for better production. If we see the details of the paper, it is a collection of data-driven collection, the data analytics, and there is some analysis that you will consider to be, okay, high number of manipulation of data is a data-driven workflow. The next paper is this paper from Raman and Sankaran they are from Anadarko. They present this automatic well interference identification and characterization, an approach to improve field operation. So basically, in this paper, they a number of probabilistic simulations in order to forecast multiple scenarios to quantify the impact of future well interference. So in this paper, very much by using the data-driven analysis, this data-driven analysis may go from establishing a neural network. They claim to have used a deep neural network. They are able to identify patterns in the flow of where to, for example, stimulate or recover production from a number of areas without doing any numeric simulation. So just by using behavior from nearby wells, behavior from previous stimulation, behavior from previous infill drilling campaign, we are able to build a nearby reservoir dynamic performance. Okay. Another example is this example from Yu and Son. It's a multi-objective optimization of CO2 enhanced oil recovery projects with a artificial intelligence approach. The whole idea of this approach is to use a number of simulations. So basically they use simulations in order to train the initial neural network. And if you see here, these are the data sets. So in the data sets, I have a number of input parameters. In this case, the input parameters were like the time of injection, the volume of injection, the place of injection. So they have 4 input parameters. And in the outputs, they had certain training targets, like, for example, cumulative oil production, the CO2 storage performance, and the overall project NPV. So this is a way to build a neural network. So if you see here, data 1, data 2, data 3, these are a number of simulations that I'm getting, let's say, from running the full field simulation. And with all these data sets, I can build a neural network. This neural network can be as simple as a backpropagation network, or it can be more complicated as a deep neural network. So depending on the nature of the problem, there is no particular recipe, one type of neural network versus another. So, but there is a continuous process of learning. So once I classify one typical problem, once I have worked a typical problem, then we know more or less how this, what is the structure that I need to use. Okay. So this is just, so typical applications in reservoir engineering is well placement, production forecast, and also NPV optimization when I have a number of cases. Another typical application is in production performance management. So in this case, I want to identify the production losses through early detection in the real-time anomalies of the wellhead pressure. So this is the wellhead pressure, and I want to identify. So the typical workflow that we see in this type of analysis is to identify and treat the data sources, perform some sort of data cleaning and filtering, and generate a time series forecasting and classification. Basically, if you see here, the first trend is the observed wellhead pressure. This wellhead pressure, as per the time series technique, can be decomposed in a seasonal stage. So this is like the seasonal stage. You can imagine that these are, let's say, day and night of the temperature and the influence over the wellhead pressure. Then I have a certain trend. So we see here, we have every 2 days, we have this date being indicated. So then we have a trend going down, and we have the so-called the reminder. So if I take these 3 signals and I add them up, I will get the actual observed data. So this technique is called time series decomposition, where I can identify the so-called outliers. So if I actual trend, so the trend is the variable that is very much containing the main signal. So we see the wellhead pressure here is around 62, 60. So, and then I'm holding here the so-called the trend. Okay, so it handles very much the average. And I overimpose over the actual wellhead pressure, I can create a model using a time series approach. So the time series approach gives me my trend, and I always subtract it from the real-time signal, and I'm able to get these outliers or any feature that I'm considering in the model. So in our case, they were able to correlate that whenever there was a decreasing temperature, a decreasing delta P in the trend, the well was normal. A pattern going up, it will refer to incrustation, and the concave downwards is interference, and the decreasing but concave downwards is paraffin. So by doing all these different analyses, they were able to classify the well, so adding and accumulating all this timing, and they were able to say, okay, based on this, there were so many, there was 5 days of normal behavior versus 8 days of uncategorized production losses, pressure decline marks. So they were able to identify when was the well most suitable for short-term intervention, and where was the well suitable for a check. Okay, most of the time, 54% with this check will determine obstruction, and in the intervention predicted by the model, 71% were predicted by were caused by paraffin. So with this one, the model was able to predict with a certain degree of confidence, around 60% of the cases, detection of choke obstruction, and this enabled the operator to minimize losses and minimize operating costs. In this case, they say we have 53% of unplanned events. So the planned events, they related to planned downtime. And out of these 53%, 67% are controllable events. So the way to use this information, I'm going to create a number of a database that allows me to detect ahead of time. I'm going to detect when this event is going to be happening, and if I can do something in my control system in order to avoid those. So, for example, in here we are seeing the spikes of current in amperage, the real power, the pressure temperature behavior, and a certain vessel temperature behavior. So by doing this and capturing these features in time, they were able to create, let's say, for example, an advanced alarm 50 minutes ahead of the failure of the particular event. Again, all of this feature detection, pattern recognition is what artificial intelligence are good at. And by doing this, they were able to save also tremendous amount of hours in downtime. Another major use of artificial intelligence is in petrophysics. Artificial intelligence neural network have been using for many years. There are thousands of papers around using neural network to predict behavior of logs, okay, and behavior of petrophysical behavior, like for example, saturation prediction, permeability prediction, using configuring a nuclear magnetic resistance log from data. So we create virtual logs from, let's say, less costly logs. So all of these have been applications that, with the use of regression models, neural networks, fuzzy logic, for many years, it have been very, very mature technology in oil and gas. So Most of the petrophysics today in the commercial tools, they use machine learning models without even noticing internally. Okay? So the whole idea for this, for example, is to predict water saturation with a small number of data samples. Area that is very much progressing in petrophysics is the so-called digital rock analysis for predicting porosity, permeability, and electrical properties and mechanical properties just by looking at the CT or computed tomography scans. So by looking at these images, we utilize a number of techniques for segmenting and fractioning the data in multiple areas without doing any particular, let's say, laboratory core flood analysis. And the major areas or other areas of growing of data in order to indicate compression and log analysis without the need of actually running the full set of log from the beginning of the overburden, yeah, on top of the reservoir section, but using other type of data such as the gamma ray or any other spontaneous potential in order to predict the compressional sonic log in above the reservoir. Other area where there is an great and advance in the use of machine learning is in seismic. The use of convolutional neural networks, which is a type of neural network that has a number of layers in between. So all of these are the so-called the convolutional layers. Then we have a series of classification layers and then as a further addition of feature detections. So the scientists are being able to more and more advance into this automatic seismic horizon tracking, fault determination, and also detection of wrong data in the seismic post transformation of time to depth seismic. Yeah. Another area is this surveillance or 4D seismic trying to determine certain patterns or certain information regarding casing failure, casing slip, cement tracking with respect to the seismic data. One of the most fascinating areas as well is the use of in drilling. So there is a number of applications in drilling. It's a very mature, the use of time series analysis and abnormal situation. For example, automation has proven, robotic automation has proven that it can take much better activities, much better performance in, for example, when we are running casing or establishing a number of running in the hole. So basically, process control is a method to improve the work step, integrating them into the overall operational activities. So this area of this is the comparison of a human-driven running casing versus a machine-driven running the casing. Okay. Another area is the use of circulating loss, and another is the use of machine learning to determine abnormal situations while drilling. Okay. Starting to wrap up. So how do we do this analysis and how do we bring this into the organization? So there is a number of techniques. The organizations face a number of challenges. So the whole idea is to pilot in small areas, supported by the corporate digital oil field team or technical center, which are effective way to initiate a transformation in a large organization. Then you gain the buy-in through all the stakeholders. Then also it's very important to have an active involvement from the leadership, where they model the acceptance from all the staff and the significant changes, the so-called oil and gas 4.0. We need to acquire and promote a new workflow profile to ensure the success of initiatives, agile and flexible. The imperative to move from traditional organizations towards new operations were more grounded into partnership, domain experts, cross-functional teams, remote monitoring, etc. The data by itself is an asset, and we need to identify what is that is the most valuable asset to drive profitability. None of what I mentioned today will happen if we don't have data, even if it is poor quality data, but it's good. And data sharing is a big step also producing breakthrough, not only internally, but across the organization. And with this, I would like to leave you some time for questions from your side. Yeah?
Thank you, Dr. Lee. Thank you. That was very fascinating to see all of the different ways. Can you hear me? I was saying that it's quite fascinating to see all of the different ways where data transformation has been taking place in the oil and gas industry, and we really appreciate your time to talk to us on this. To summarize, if I could, there were a lot of things that were a bit like over my head, sort of. But I mean, for me, I'm quite new to this. I did a bit of neural network a few years back, but that's about it. So for me, a lot of the things were kind of quite new. I mean, I've seen in the news and papers and all of that, but I haven't really paid a lot of attention. To summarize, you've shared with us the different categories of technologies available, starting with the AI, machine learning, analytics, and you also talked about deep learning, and you talked about robots, general artificial intelligence as well. You mentioned the chatbots and the BOTs as well. And yeah, so quite a couple of categories. And then you went on to talk about the applications of the different technologies. So you shared some SPE papers, which we've seen some. For me, I wrote down some of the numbers so that I could go back and read up and get a bit more understanding on what they did. So aside the papers you shared, you also went through a few of the domains. So you looked at, for example, production, how to identify. There was a case of where production losses were identified via wellhead pressure. I also talked about a case where there was unplanned shutdown and how the AI helped, to train the data and all of that, and they were able to detect events long before, or a couple of minutes or whatever before they actually happen. And then you also shared some cases from Petrophysics domain as well, of how neural network has been used to predict behavior of logs. An example was the water saturation log that you shared with us as well. And you also went into the seismic domain as well. I'm sure the seismic guys will be excited as well to know that they can use this. So you talked about how they used a case where they used convolutional neural network to track horizon from seismic images. Then you went on to finally summarize that, how we can actually bring all of this into different organizations. So you mentioned that it's a good idea to start with a pilot in a small area. So instead of, trying to do it very big, no, you recommended that it's better to try a small area and then get the corporate buy-in before trying on to, the other aspects as well. You've also said that we should, that it's a good thing to move from the traditional way of, for example, detecting events or production issues, etc., to more modern ways of doing things. And another point you also mentioned was that all of this, which is for me a big thing, all of this requires requires data. So no matter how small or how no matter how small or how big the data is, it's very important because I mean, without data, we really don't have anything because we need to train all of these different technologies to be able to predict for us. So I think with these few points of mine, I think I've kind of summarized your presentation. I've tried my best, and yeah. So I'll open the line just now for questions. So I think I'm not sure who's Mohammed. Please, could you remove your video? You're sharing your screen if you don't mind. Okay. We'll open the line so that if you have any questions, please feel free to put it in the chat room so that I can read it out for the presenter to help us answer. If you have any question at all, please feel free to type it in the chat room, please.
Yeah, so one of the questions there is having materials for the lecture. I'll share you the slides, and I'll also add a couple of slides that I couldn't time to integrate it here regarding resources. Yeah, if you want to have start getting more information, there are hundreds of courses that we can get from the internet, many of them for free, and some of them, one of the best universities, you can also get certificates for a small amount of money, like from $40, you can get a certificate from Harvard University if you want to, all from your home. Okay, so all of these are very useful. And also SPE has a lot of materials. I will share you the links if you want to participate. There is a predictive analytics section. There is a data science and engineering magazine happening every month. And there is a lot of, there is a website where you can pose your questions if you are lost. And you are also welcome to ask me anything. And I will be glad also to come back to one of your webinars and give you a walkthrough example. Yeah.
Will you be sharing this the links, a couple of these courses?
Yes.
It's easy for everyone to know where to go to. So do we have questions for Dr. Luigi now? Dr. Luigi, if I may ask, you had an initial example that you showed before you showed the SPE papers and all of the different cases. About, you know, having like 4 wells, you see the rates, the water cut is high, medium, etc., DGOR, the status and all that.
Yes.
The final well was going to, like, based on what, you know, train the AI with past experience, then it can predict what's going to happen in this other, the 5th well that you showed.
Yes.
So I was just wondering, if you look at it, if you see the water cut, the GOR, and status, you know, all over the place, as in you've got high, you've got low, you've got medium, etc. I know if you have a lot of data, yeah, it will probably help you. But if you don't have, like you just have a couple here, how do you how are you able to predict the status? Because a well might have low water cut, high GOR, but in your case here is healthy, but in another case it just might not be healthy as well. It could
Yes.
be, I don't know, something else. How are you? How is the AI able to predict what this 5th well will do, just based on just a couple of data here?
So put this example, which is simple, but at the same time a little bit dramatic, no? But it's the reality. Just to show you that the where machine learning and classification algorithms are good is in classifying data that humans will not easily pick up. Maybe one experienced engineer will know that the ratio of, for example, high GOR with a low productivity is related to a gassy well in a particular field, okay? And maybe I know that a high GOR with a low water cut, and it's a sign that the well will also get unhealthy in the future, yeah? So that's why I want to decrease the rate. So the solution for that, I mean, it can be done with a so-called cluster classification. Yeah, so that it will group the wells in 3 these variables. So I can get up to 5 different clusters. Yeah, but I want to classify the wells into healthy and unhealthy wells. And if it is healthy, I want to classify it in the wells that need to increase and the wells that need to decrease. So basically, with the 4 rows above, I will construct what is called a decision tree. And with that decision tree, I will come out with a number of probabilities. So what is the probability that when the well is high and medium GOR and is healthy, I need to increase the production? So those will be the type of analysis that comes to this mine. Now, so there is no particular solution that I was intended to show in here. It's just the ability that there are classification methods, there are classification problems that are not common to the human eye. Okay?
Okay, all right, thank you. So we have a couple of questions here. So the first one from Ayo says, do you recommend building models from scratch, R or Python, or customizing commercial software for oil and gas applications?
Okay. In my opinion, I like to build them from scratch. Yeah, of course, an organization needs to have a number of base foundations. So the main base is to provide the tools and to provide the so-called development environment. And if the tool is going to be implemented in a time operations environment, then a number of IT support foundations will be required. Yeah, like having the tool needs to be protected and it has all the securities and it has all the database access, the maintainability criteria, etc. But today is so easy for any engineer to work in his own machine, uh, taking a subset of the data and performing a quick analysis or a quick program using R or Python. So we're talking about few lines of codes. Basically, it will take, yes, an engineer will have to learn the basics of programming, okay? The basics of establishing a small script or establishing a small script. If you don't like programming, then there are other tools that allows you to work more into the workflow automation type. Some of them are also free, like a RapidMiner or NIME, or even Microsoft and IBM. They have tools that are up to a certain point, they're free, and you can build your own machine learnings without any single line of code. But if you like to program, and if you like to ever build like a small macro in Visual Basic in Excel, then R and Python will not be that difficult for you. The important thing is that R and Python are the most powerful toolkit available today to anybody in the world. They are free. There are millions of resources. There are millions of people doing the same thing around the world. And it's a way to become competitive. It's a way to build something from scratch, leveraging a lot of resources around the world and without having to spend a single penny. Okay. So it's a very, and so you can go from training yourself, getting access to resources, establishing your own first program with your own resources. Yeah.
Okay, we'll take just a few more questions, like 2 or 3, so we can round off.
Yeah.
One here that says from me Adage says, what should be the progression or learning into machine learning for a beginner? What do you recommend? Where can they start from?
Okay. The best progression, I will send you a quick slide, but I will send you there are 1 or 2 courses from reputed universities, from MIT, from Harvard, from Hopkins University, and from Stanford University. These are courses that will take minimum 40 hours. You can do it in a lapses of 6 to 8 weeks, which will give you a walkthrough from the beginning to the end about all the basics of machine learning and artificial intelligence, to how to download the tools. They will give you access to a lot of examples, and you will build up to a certain level. So this will be my recommendation if you want to get seriously trained. Now, there are a number of another videos and short courses and around in the web as well that it will give you and take you close to learning the basics. Okay, so if you are a manager or supervisor, or you just want to get acquainted of all the different methods, there are also very light. So in my suggestions, if you are a young engineer like me, you have 30 years experience, you still have chance to learn the basics of machine learning and analytics. You will use that into your life. Not only if you are in the petroleum engineering, but if you want to go and do business outside, anything that is related to marketing and everything related to, if you are a doctor, you need to know these tools, because this will be extension of your capabilities. Yeah? And there is a question there about poor data and good data. Yeah, some machine learning models are more sensitive to errors than others. Are there particular guides which model to use and which not? So it's not exactly a particular guide, but more will go into very deep neural network models. For example, to recognize images, to recognize, for example, to determine a fault in seismic data, to determine poor quality data in log data. These new models allow us to identify good quality versus poor quality. Now, from the traditional tool, statistical models are used to determine outliers, to determine data that is not relevant or not well correlated. So there are many tools to determine that, and there is not a particular rule for.
Yes.
I think one final question.
Okay.
Just somebody that said he didn't really get the part on the drilling in respect to time series. I think one of the case studies you shared was on drilling. So I don't know if you could quickly summarize it for Frank.
Yes. So very quickly here in drilling, the real time series or time series is the most common in whenever we have source data from the surface parameters. Yeah. In this middle example, let me see. In this example here, we are cleaning the data from, let's say, the lost detection system. So basically, when we are detecting gain and losses in a fluid circulation system, we are very much not able to recognize when are we actually gaining fluid in order to detect a kick, okay, or to detect a serious influx. So by using machine learning, in this case, they were able to reduce the noise. So we eliminate the noise of the data. And then in here, before we need to have a threshold of about 180 barrels of gain and losses in fluid. So basically, we were not able to detect a kick or a normal situation, even with this amount of noise. By applying machine learning and cleaning this, threshold was able to be reduced around 25 to 80 barrels per minute. So we're much able to determine a kick or an abnormal situation than with a normal, without the machine learning model. Another application here is to, for example, they took data from 40 different access types in thousands of wells, and thought about what are the patterns that will that will particularly follow a particular accident in a field. Like, for example, the probability of having a breaking in the oil stream, a probability of a washout or a pipe stock or differential sticking. So by looking at all these different accidents, the system is able to predict about a great number of accidents before they occur. And the other application is to determine severe dynamics abnormal situations like whirling and high frequency torsion resonance or any particular. So again, the same thing with the amount of training data, we are able to determine particular situations in the dynamics world. And then once those dynamics are determined, for example, in this case, the red part here indicates the probability of high torsion and whirling occurring in the pipeline. So then we're able to do something about it in order to prevent any major catastrophic. And in drilling, there are many applications in regards to detection of stockpile, detection of lost circulation, optimizing of weight on beat. So these are all techniques about using data and building predictive model and optimization in order to improve the drilling performance. Yeah.
Thank you so much, Dr. Luigi. I think that's about as much question as we can take. We need to end this now. We'll share the materials, we'll share the links, we'll share the recordings, and if you need to ask Dr. Luigi a question, then I think he will be nice enough to share his email address so questions can be sent to him.
Yes.
Yeah. Okay, thank you so much. So before we go, I just wanted to mention that the community section, the community chair for Lagos SPE, there will be a beach cleaning initiative that will be happening sometime soon. Please, everyone, please watch out for the announcement and please join us on that day to help clean up a bit of the beaches and Lagos, okay? All right, everyone. Thank you so much, and apologies again for the late start. I think it was interesting enough to keep us listening. So thank you, and do watch out for the next webinar coming up soon.
Yeah.
Thank you. Take care now.